Assalamualaikum. Welcome to all. I'm going to summarize what you learn in the experiment: losses in the bands and pipe friction. Okay, our experiment or lab teaching is based on inquiry guided. Okay, in one go, we don't give you everything. So you do experiment, you try to observe, find some facts right away in the lab, and then you move on. You process your data, analyze, try to get some information, try to get some results, and so on. Okay, so first of all, let me talk about pipe friction experiment. So your first observation was you connected the manometer across the length of pipe. Okay, like this. Pipe is there, then there is manometer here, and then there is downstream manometer, right? So there is a flow of water, then this height you measure, isn't it? H1, and then flow H2. So H1 is more than H2. So this is P1, P2. Okay. So H1 is more than H2. So there is loss in pressure, head loss, pressure loss, which is happening just because of friction in pipe. There is no other reason. So okay. So as fluid flows along length of the pipe, there will be pressure loss because of friction. Okay, this is the first observation. You all of you know that. Okay, but what about if I increase the flow rate? The second observation, you got it in lab right away that okay, if we increase the flow rate, the difference between H1 and H2, delta H increases, right? So increasing the flow rate, increasing the friction, increasing the pressure drop due to friction. Why? Because at higher flow rate we have more friction and we have more pressure drop. So what next? To establish a relation between delta P and Q. Okay, this is increasing, but what the relation? Is it linear, quadratic, polynomial? What what do we have? Why we want to establish a relation? Because to see that okay, if at this flow rate pressure drop is this much, what if I double the flow rate? If I double the flow rate, is it going to be doubled, or it will be 8 times, or it will be exponential, or what? So delta P versus Q, you had the data, right? Delta P versus flow rate, and you found that okay, all the data point are in turbulent region. So you had this one. Some of you fitted linear straight line. So I ask you to think about this. Turbulent flow is not linear, is like approximately delta P is proportional to Q square. It means that if you double the flow rate, your pressure drop due to friction will be 4 times. Okay, why? How we can in turbulent region? This analysis depends mainly on experiments. Okay, so you do experiments, try to get the correlations and so on. But again, we can establish a relation. For example, I ask you to do in its HYSYS laminar because we could not get it in turbulent. So you've run the simulation for Renault number less than 2000, couple of data. Okay, some of you did that, and you found that delta P is linear with Q. Delta P is proportional to Q. It means that this is laminar. Okay, laminar. So laminar flow is smooth, slow. So increase in pressure drop is not that much. It will increase if you double the flow rate, pressure drop will be doubled. Okay. Now, how we can get this relation? In laminar, we have exact equations. Okay. So delta P versus Q. I am giving you exercise. Okay. How we can relate delta P and Q, assuming everything constant. We have two things. We have in laminar friction factor 16 over Re. Okay. And then the definition of friction factor is delta P is delta F is delta P over 2 rho V square D over L. What you do, you combine these two values. F 16 over R equals delta P divided by 2 rho V square D over L. And then see what exact relation you are getting. Okay. So F is 16 over RE. RE is basically V D rho mu. Okay, I'm not going to solve it completely. I will leave for you. Please do analysis work with pen and pencil. Okay. So this is 16 over RE, and then we have delta P over 2 rho V square D over L. Okay. So now V is also a function of V is Q over area. We're trying to get delta P and Q. So where is Q? Q is here also. So replace this and then see, establish a relation between delta P and Q. So you should get delta P. You will have other factors but proportional to Q. I leave it for you. This is for laminar. Okay. So in laminar linear, pressure drop versus flow rate is linear. So if you double the flow rate, pressure drop will be doubled. Similarly, in turbulent region, we have a lot of correlations. Okay, one of the simplest correlation is Blasius, right? This one we used also in lab. F is 0.79 RE power minus 0.25. Okay, and then we have same. So delta P over 2 rho V square D over L equals this. Do same analysis, roll number, change in velocity, diameter, and so on, and see the relation between same velocity here, Q over area, and see the relation between delta P and Q. Not only delta P and Q, you can get the relation between delta P and diameter also. Okay, so you will see that delta P is proportional to Q, something like this, 1.75. Okay, so it's approximately 2. So in turbulent region, what we have higher, we increase the flow rate, friction increases too much, so it's become like a square. If you make it 3 times, the pressure drop will be 9 times 3 square. Okay, so this is about relation between pressure drop and flow rate. Okay, and now let's see, we have also pressure drop versus diameter, the same analysis. So at the fixed flow rate, you did this, right? At fixed flow rate, you calculated the pressure drop due to diameter, sorry, pressure drop due to friction versus diameter. So the same analysis you did here with if you plot delta P versus Q, 1 2 3 4 diameters, D1 D2 D3, D1 D2 D3 D4. Okay, can you tell me which one is, what is the order of diameter? So smaller the diameter, more is the pressure drop due to friction. Okay, so D1 is highest, so D1 is the smallest diameter, D1 is less than D2, less than D3, and so on. Why? Pressure drop decreases with increase in diameter. So we are fixing the flow rate. So we are fixing the flow rate. It means that if at fixed flow rate, we increase the diameter, so velocity will be, we increasing the diameter means increasing the area. So area increases, velocity will decrease. Velocity decreases, it means the friction will be smaller, pressure drop due to friction will be less. So now we want to establish a relation between delta P and Q. It's like we want to quantify, okay, if we change the diameter, how much pressure drop will be less or more. For this one, what you can do at a fixed flow rate, suppose at this value, get all these values, delta P1, delta P2, delta P3, delta P4, or just as you did in HYSYS, change the diameter and get the P1 minus P2. So relation is interesting. So if you plot delta P versus diameter at fixed flow rate, your data is like this. It means that the sharp decrease in the pressure drop. So a small increase in diameter will decrease the pressure drop too much. Okay, and if you fit a power train line here, delta P is proportional to d power minus 4.75, something like this. So it is basically 1 over d power 4 or 4.75. Okay, so d power 4 for laminar, but this one around 4.75, something like this. So small increase in diameter will decrease the pressure drop too much. So this is the relation between delta P and diameter. Okay, so these were like summary of the findings what we learned in pipe friction experiment. The next in next video I will do it for pipe losses in the bends. Okay.